Okay, what I'm excuse me, what I'm going to do here, rather than doing this through PowerPoint, is I thought it'd be interesting to actually look at doing a simple example, a fairly simple example in this case, directly in the software, so you can sort of get a feeling of how we would maybe set a model up and look at a problem. Now, the problem we're going to look at here is a very simple problem, just so we can easily look at a few different variants of the model and get a good idea of what's actually happening and hopefully why it's happening. So this is the structure we have, and I'll start off just by briefly describing this structure, and then in the subsequent models, just describing what the differences are, and then we can see how that changes what's actually coupling. Now, of course, one of the beauties of doing lightning strike analysis in a simulation environment, in a modeling environment, is that, you know, if we're doing something like an aircraft, for example, which is flying, we can actually simulate it being in the air. Whereas when you do the testing, of course, the plane has to be stuck on the ground, which is obviously a different set of conditions. Now, when we do the analysis on the ground, typically we would set the structure up. So it's actually in this example, it's this box in the middle here, which we're going to apply the strike to, and we've got a return cage, a current return cage around the box here. And of course, when we do the strike analysis in reality, we've got to have this return cage to obviously inject the current and obviously have the return path for ourselves. Now, the way this model's set up, I'll show you what's inside the box to start off with. What we've got inside here is a very simple structure. This is at the moment here, it's a PEC enclosure, so it's a perfectly conducting metallic enclosure. There's no holes, no discontinuities, nothing on this box at the moment. Inside it, there's two other enclosures. These are just solid enclosures connected. You can see here connected to the outer enclosure, and then between them we've got a cable running, and this is going to be a coaxial cable, which again I'll show you in a moment. And what we're going to be interested in looking at is calculating the current which couples onto this coaxial cable by means of the lightning strike. The strike is being injected from our ports over here, port number 1, and we're going to obviously monitor the current at this point, and we're going to monitor the current at this point over here as well, where we've got the exit path or the detachment path. Monitor the current here as well, and then we'll monitor the current both on this the screen of this coaxial cable, but also on the inner conductor of the coaxial cable. The other place where we're going to monitor the current is on this return strap here at the top, and also on the return strap on the side here, so we can get an idea of the amount of current which is flowing down the different straps. Now, in terms of this model, it is pretty much a perfectly symmetrical problem, but it's just not quite symmetrical, as we'll see when we actually look at the results in a moment. In terms of the actual source signal itself, it's obviously of the form we have here. This is the typical waveform which we'd be using for doing lightning strike analysis. You can see we have a peak amplitude here of 200,000 kiloamps. 200,000 kiloamps, and we've got a rise time of the double exponential of something in the order of about 1.5 microseconds, and the decay time is around the 88 microseconds or thereabouts. So it gives us this overall waveform shape, and this is applied as a direct source on that excitation port. So if we go back to the model again for a moment here. So as I said earlier on, this enclosure at the moment is a PEC enclosure, so it's a nice, highly conducting enclosure. The ground strap system as well is a PEC structure, as are the boxes inside. So as our sort of start point, our reference point, we have a very well controlled system here, where hopefully we'll be able to see some nice current flows through the different parts of the system. So in terms of running the analysis, it's obviously a very straightforward process to set the model up and run the analysis. And what we're interested in, of course, is actually looking at the currents which we get. So in terms of the results, if we just look at the current distributions, so there's 8 currents which we're looking at here. We're looking at the feed current, the exit current, the top strap and the side strap, and then we've also got the current on the screen, either end of that inner cable, and also on the inner conductor of that coaxial cable. Sorry, I should have shown you maybe the setting for the coaxial cable first. So if you actually just go back to the cable here, so you can see this is defined as an RG58 cable. We actually just have a quick look at the properties for this. You can see what we've done here is we've set the braid diameter, the inner wire diameter, the permittivity of the inner dielectric, and also the transfer impedance of the cable as well, to allow us to get the current which couples from the screen to the inner conductor. So in terms of running or looking at the results, what we can see here, if I just show the feed to start off with, let's just look at the feeds. So that's the current which we've got at our feed point, which obviously equates to the source current which we specified earlier on, the double exponential source current. At the exit point of the cable, so at the far end, we have the green trace, and you can see that sits pretty much identically on top of the source current, because again we've got this very well controlled system here. If we then look at the two return straps, if we look at the top and then the side strap as well, we'll put those on with the source currents at the moment. We can see that they're both in the order of around 50,000 amps down here. So roughly a quarter of the current is coming back on each of those straps. Interestingly, if we just, as I said a moment ago, if we just look at those two on their own, we can see there's a very small difference between the amount of current on those individual straps. And that's just purely because of the way I set this. I've set it to be very slightly asymmetrical, just so we do see a slight difference on those two currents. But nominally, we could say for this problem, it's identical current on each of those four return straps coming back around the system. Now, what we want to understand, of course, here is what's coupled to the inside of the enclosure. What's actually coupled onto our cable on the inside. Now, if you remember, I mentioned that it's a PEC enclosure which has no holes, no discontinuities, nothing like that. So if we look at the current on the screen of our cable, unsurprisingly, for both ends of the cable, we've got absolutely zero. So nothing's getting inside this enclosure at the moment. So this just gives us, to start off with, a very nice reference, which allows us really just to sort of ensure that the whole setup, the source and the return cage characteristics are behaving as we'd want them to behave. We could also look at the inner conductor currents, but it's going to be zero as well, so we don't need to worry about that. So what we can now go on to look at is say, well, we can change this structure now. So instead of having just this perfect enclosure, what I'm going to do is actually put in a couple of discontinuities. I'm going to do this by inserting just a couple of thin slots onto the enclosure. So it's still going to be a PEC enclosure, but what we've now got, I'm just showing one of them in the image here, this green line down here, this is representing a slot. So you can imagine we've just cut a straight slot down the side of the enclosure here. Other than that, everything else in this model is exactly the same as the previous reference case. So we can go on and we can start to, again, look at the current distributions, or the current profiles which we get. So again, we can see here at the top here in green, and obviously the red one behind it, our feed and exit current, again around the 200,000 amps. And again, on our two return straps, again in the order of the 50,000 amps. The interesting thing now, of course, is to say, well, if we remove those currents and we look at the inner wires, do we get any coupling onto that inner wire? And from this spot here, we can see we do. So what we're looking at here, the pale blue curve, and again this is looking at end 2 of the cable. End 1 of the cable is the same current distribution, and we can see we're getting about 300 amps, or just under 300 amps, coupled onto the screen of our cable. This is purely just by introducing those very small discontinuities into the wall of the enclosure. And this gap is only about maybe a 5 millimeter gap or so, which has been introduced there. But as soon as we get that discontinuity, it's allowing obviously the current or the field rather to couple into the enclosure through the gap. We then just look a little bit further and say, well, if we know we've got let's call it 300 amps on the screen, we can then look at the inside of the cable as well, look at the inner conductor, and we can see the current that we've got on the inner conductor here. So we're, through the transfer impedance, we're able to then calculate, say what's on the inner conductor of the cable, and we're getting somewhere in the order of what's that, about 25 milliamps or something like that on the cable. So from our start point of our 200,000 amps, we're now down to 25 milliamps actually coupling onto the signal conductor itself. Now, what's interesting to actually go on to do here is say, to actually look at the field and the surface current distribution actually on the 3D geometry. So if we just look at this in the time domain, so we can actually see the current moving through the strike. I'll just wait for this to load a second. Hopefully, won't take too long. Here we go. So we've got the structure here, and if we just run the animation here, so we actually see the current increases very quickly and very dramatically around the enclosure. These sort of two blue areas here, these are where the slots are sat. And we can see obviously just the current distribution. This is running up to 100 microseconds. If we'd run it longer, we'd have seen the current reducing again. But we can start to see it reducing when we look at this animation here. What we can then do is we can say, well, let's look at the maybe the vector information associated with the surface current. So again, we can see here, this is obviously our source point. We can see the current is flowing this way across the enclosure, and then back around on the return cage back to the source point. And again, we can clearly see that the predominant amount of current is on the inner side of the return cage here, rather than the outside of the return cage. And if we just turn those vectors off for a second, if we just change the scaling here a little bit, what we'll see is obviously, at these edge points around here, we're obviously seeing a much higher level of the current, because obviously as the current is flowing over the enclosure, when it gets to the discontinuity of the slot, it can't flow across the slot, it has to go around the slot. And obviously, as the current flows around the slot, we get the higher density of current at the either ends of the slot, which obviously allows the field to establish itself across the slot and then couple into the enclosure itself. So if we actually look at the field which couples into this enclosure, so we'll just put that in the middle there, change its color map, and we can see here the field that's coupling in. So the return cage, we can see, actually has a fairly good level of control of the field. So we're not getting a lot of field radiating outside of this overall structure. Most of it's fairly well contained inside. And if we actually just remove the surface currents for a second on the enclosure, we can actually see then inside the enclosure itself. So the field levels inside here, this is looking at the magnetic field. The magnetic field inside the enclosure is pretty low in comparison to what we have outside. Here we can see the surface currents on the two internal enclosures, which again is very low. But if we just again modify the data range a little bit, we'll start to see now here the field which is coupling in through that slot. So you can see this sort of, I guess you could describe it as like a little U shape of field coming in here, and this is as it comes in through that enclosure, through the slot in the enclosure, and then we can see obviously the field coming down here towards the wire, and then obviously that's how the signal's getting in and it's coupling onto the cable inside the actual enclosure itself. So in a very simple example here to start off with, we've seen how we can go from our perfectly shielded box to one where we've got the very small discontinuity, and how that actually makes quite a big difference, in terms of the amount of field which couples into the box, and therefore the amount of current which couples onto our internal cables. And obviously it's the coupling to cables which is very important. That's what we really want to understand, that the cables are connected to the different systems in the device which we're looking at. And again, we'll see later on how we can do more complicated cables with multiple conductors and different cross sections. So that's looking just at a simple problem there where we've got that metallic enclosure. If we actually take this on now and say, well, let's do something different. Instead of having a nice enclosure like that, where it's a PEC enclosure, of course, in reality, we don't have materials that are PEC. we have real metal, if you like, running around a structure. So we've got one here, which is again exactly the same geometry, but this time instead of being a PEC box, it's now made of aluminium, and this aluminium is only 100 microns thick, so it's very thin aluminium in this case. Again, I made it fairly thin here just because it gives us a better result, if you like, in terms of looking at the coupling onto the cables. So again, the aluminium of this box again is modelled as what we're calling a thin panel. So we define the properties. So we've got the conductivity of the aluminium here, roughly 3.5 e to the 7 Siemens per meter, and our thickness down here of 0.1 millimeters, so our 100 microns of thickness. Again, other than that, it's exactly the same setup as in the previous models. We don't have the slots in the enclosure here. So this is now equivalent to, again, to the first model which we looked at, the perfectly sealed enclosure, but all we've done now is instead of having a PEC material, we've made it a real material, for want of a better description. Again, when we look at the current, we can see the same sort of idea. Again, here's our injection or our feed current and our exit current, and here's the current on the two straps. Again, they're all still in the same sort of orders as we're seeing previously. What's interesting to look at now is actually how this is changing the overall coupling inside the system. So what we see now is actually quite a difference compared to what we had previously. The trace we can see here, this pale blue trace, and again there's an orange trace underneath it. This is the current on the inner screen, sorry, on the screen of the inner cable. So whereas what we saw before with the original problem, we got no current. With the one with slots, we got a current which followed the source current fairly well. What we see now is a current which, even after 100 microseconds, is still increasing. So even though our peak is after around 6 to 7 microseconds of the actual lightning strike itself, because of the diffusion through the metal here, it's slowing down the coupling onto that internal cable. So it's taking a lot longer for it actually to reach its peak. And I could have run this model on for maybe another 100 microseconds or so, and then we'd have seen the peak and started to see the current hopefully starting to tail off. And the same is true again here if we look at the coupling to the inside of the cable. Excuse me. So again, we've got again this much slower coupling. With the slots, I think we had the order of, what was it, about 25 milliamps peak. We're now to around 250 milliamps, and again, we still potentially haven't reached the peak current. Okay. So again, what this is allowing us to see here is to get a really good idea of how the current from the source is coupling onto the, or coupling through the structures, coupling onto the internal cables in this case, and it's really giving us a good idea of the amount of current which is coupling through the box. Now, the final example which we're going to look at for this problem, again, as with all the previous ones, is exactly the same structure, the same dimensions. I should have said the dimensions of this box, it's relatively small. The inner box which we're looking at here, it's only around 1 meter or so in length and about 0.5 meter square. So it's not a huge problem which we're looking at here physically. And then the ground strap itself, this is around 2 meters in length. What we've got now for this box is in the middle here, instead of being a metallic enclosure, it's now a carbon fiber enclosure. And the way we're modeling the carbon fiber is in exactly the same way as the thin aluminium. So again, we've defined its material properties. We've kept its permittivity and permeability at 1 here, giving it a conductivity of 10,000 in this case. So quite a low conductivity. Again, if you look at different papers, you'll find a range of different conductivities for different composite materials. But you can see here the thickness is quite large. 25 millimeters thick is our composite material in this case. So we're talking, in old language, an inch thickness. So it's a not insignificant thickness of material which we're looking at. And again, we're interested in exactly the same way to see the current which is coupling to the inner cables. So again, if we can look at the results of this one. And again, as we've seen in the previous examples, our feed current and exit current around the 200,000 amps. Our strap currents, again, around the 50,000 amps. Again, we can remove those from the plot. And what we now see is we're now looking at the current, again, coupling through to the screen of the cable. Again, it's even after 100 microseconds, it's still not quite reached its peak. But we've got a lot more current coming through now. We're now in the order of what's still around the sort of 25 to 30,000 amps coupling onto the screen of the cable. And again, in the same way, if we take the inner conductor of our cable here, we're now up to something in the order of 2.5 amps. So when we started off with our original perfect box, of course, there was nothing. Put the slots in there, we were around the 25 milliamps or thereabouts, peak current. With the 100 microns of aluminium, we're in the order of around 250 milliamps, and we're now in the order of around 2.5 amps. So you can see as we're making these very small changes to the structure which we're looking at, the way the field is coupling, where the current is coupling through to the inner cables is changing quite dramatically, and the levels of coupling we're getting are quite significantly different each time. And this, of course, is particularly important, excuse me, particularly when we're thinking about aircraft and modern aircraft, where the amount of composite material is increasing dramatically on aircraft, that the coupling which we get through is obviously going to be a lot higher than we were getting with traditional metal fuselage aircraft. And what we can see here in the software is we have the ability to look at these different material properties and understand how the different properties are allowing us, how the different properties impact on the amount of current which is going to couple through and couple onto an internal cable. Again, as I said, for this example, we've looked at a very simple problem because it's allowed us to really sort of understand the problem quite well, rather than doing a very complicated structure, and just to see how just these simple changes are making an impact in terms of the results which we see. And again, in terms of modelling the composite here, we've modelled it as a bulk material property. We haven't taken into account different weave angles, for example, because we're looking at it at a much larger scale than we'd be interested in for going down to that level of detail on the material properties. So that's what I wanted to show briefly this morning. I've sort of gone through that fairly quickly, I guess. But maybe we have a minute or two if there's one or two questions on that. On these straps here, yeah. This is I've done using the new 2011 version, a beta version of 2011, and this is using a current loop in effect. It's what we call here a current monitor. So basically, what I've done here is I've just defined a path around this, and then defined that path as being wanting to get the current on that path. So that basically what it does is it takes it calculates the total current cutting through that loop. I mean, it's a very thin rectangular loop which we've got here. Yeah. In effect, yeah. So it allows us to get current flowing on individual paths. So again, we could have put a loop around the whole structure, and that would have given the current flowing around the whole structure, which in theory probably would have come out zero because of the different directions of the current. Last version 2. Was it? Right. Yeah, I mean, this is just doing it as a straight current monitor here. So you just say, I want the current running around here. Do you use only the TLM solver or another solver? This is solved using the TLM solver. So I tried the tank with the function solver, and I got a big problem with oscillation. Because the feeding house of the lightning part is very unpredictable because there's a very short rise time, and what I got is
oscillation, and I wonder why you got almost no oscillation.
Where are your it might depend where your oscillations are occurring. If you actually look at the current at this point here, you do see a little bit of oscillation on the current here. So if I just show you that one on its own. So let's take those two off. Let's just put the exit current on. I'll just zoom in on that area there. So there's a little bit of oscillation here. And to be honest with you, I've not looked into the detail about that yet, but my suspicion is that it's a resonance effect of the length of the cage here, because we're just seeing a slight ripple there. Sorry?
I have no cage.
Right.
And electrical background properties and parts the current can.
So you had electric boundaries. Well, that's forming your cage then, in effect.
Yes, it was.
Yeah.
But it was not such a cage.
Mm.
More questions?
The blue lines here are the wires which are injecting the current. Yeah, what you have at the red point here, this is the actual feed point. So this is where the current is being generated, if you like, and then this is the path that the current is going to flow down. So this is injecting it onto the actual box itself. In the previous example it was, yeah. I don't think so, no, because I mean the current effectively is just it's just flowing around this whole loop here. I don't even see the reflection because there's not a real discontinuity as such. I don't think. The mesh. Again, the mesh is based, as you're used to using it, it's based purely on the frequency you want to look at. So we know from the lightning strike waveform that the frequency component is relatively low. So you can obviously mesh to a relatively low frequency, maybe something in the order of say 30, 50 megahertz, something like that, typically. Again, if you've got a larger problem, maybe you can go to a slightly lower frequency. If it's a smaller problem, maybe a slightly higher frequency on the meshing. But again, the key thing is because of the frequency components of the waveform, which you've Fourier transformed, everything's gone within a megahertz or so, typically, a few megahertz. Okay.
Good. Thank you, Paul.